This is a video about moment of inertia. When we started doing forces, we said mass was kind of the big resistance to acceleration, and now we're doing the rotational version of that. So now we're going to talk about how moment of inertia is the resistance to angular acceleration. What we've done so far with rotation is we have had theta, omega, and alpha, which were just rotational versions of a position, a velocity, and an acceleration. Then we said we're going to take force and turn it into torque. And then we did these rotational equilibrium problems where we said effectively the sum of torque is zero. But after we did forces with linear motion, we said the sum of forces is mass times acceleration and use that to find acceleration. These were not static cases anymore, but dynamic cases. And so we should have a rotational version of this too. Force becomes torque, acceleration becomes angular acceleration. But what about mass? If we have a bar like this and we hold on to the end of it, if we want this bar to rotate and we apply a force here versus here versus here, we get different amounts of acceleration because of the differences in torque. What happens though if we have this bar and put the axis here versus if we have this same bar and put the axis here? Well, this bar is easier to turn. And the reason it's easier to turn is because of something we call moment of inertia. The total mass of the bar is no longer the only thing that matters. The other thing that matters is where we put the axis. So that's what moment of inertia is a resistance to angular acceleration, and it depends on the location of the axis. It actually depends on the entire mass distribution around the axis. So this is my moment. For a single point mass, my moment of inertia is going to be m times r squared. What that means, if I've got a location that is an axis like this, and I'm trying to rotate this point mass around it, I'm going to get a moment of inertia of mr squared. Now there's not really a good way of doing that because, well, it's not fixed. But if I have like a very light rod, maybe this is a rod with a mass of, 10 grams, and I attach to that a big mass of 20 kilograms, then the rod doesn't really factor in very much. And talking about this as a point mass would be, not 100% accurate, but it'd be pretty close. It would be a good estimation. So that's how I might look at moment of inertia of a point mass. If I have more than one particle, if I have like a couple particles, call this thing M2, this thing M1, R1, R2, now my moment of inertia total is going to be m1 r1 squared plus m2 r2 squared. It's just a scalar quantity and we keep adding. There's not really a good way to take away from the moment of inertia. There's definitely not a way to take away from the moment of inertia by increasing the mass. If this is an mr squared, that means we get units here of kilograms, units here of meters squared, and that is our unit of moment of inertia, is kilogram meter squared. Now you might think to yourself, yeah, that's great, but how often are we going to get single point masses to figure out moment of inertia? Isn't it likely we're going to have actual shapes too? And the answer is yes. If I have a disk which is a solid cylinder, and I stick the axis through the middle of that disk, I could say right? First I can say this disk has a total mass m and an outer radius, a full radius of capital R. Now I could make this disk out of a bunch of little point masses. And for anyone with some amount of calc background, you see where this is going. When I take the moment of inertia of all of those little point masses and add them up, what I end up with is a moment of inertia for a solid cylinder. That's what this is. Of half mr squared. It doesn't matter what the height of this cylinder is, because for every point that I've got here, I've got another point directly below it, and those points are going to be the same distance from the axis. What I'm worried about is the distance from the axis. So if I have that cylinder, or if I have a cylinder that's taller, I know I didn't draw these to scale, but let's pretend for a moment that those are the same. I can make this with a little point mass here on the edge. Here's a little point mass directly underneath it, where this is the full distance from the axis, this is the full distance from the axis. So instead of making this out of point masses, I might be making this out of just like point columns. The idea really being the moment of inertia doesn't depend on the height of the cylinder. We don't really care. That's for a solid cylinder. What if I do instead a hollow cylinder? So there's that part, and now I'm going to look at it as a hollow cylinder or a hoop. The hollow cylinder, if this is made with a mass m and a radius r, I guess I can do this, right? Mass m, radius r. The hollow cylinder looks a lot like the solid cylinder, but it's made of particles that are all out on the far edge. I can make the hollow cylinder out of the solid cylinder by removing these particles that are closer to the middle. Now the particles that are closer to the middle, if the moment of inertia of a point is going to be mr squared, and I'm going to remove the particles that are closer to the middle, then that means what I will be left with is a bigger moment of inertia. Now that's only because these masses are the same. So if I'm going to have the masses be the same, then this one might be made of something lighter, like a light wood, and this one might be made of steel or something, because all of the mass is out of the far edge. But if I'm going to take all of the particles that are, and maybe that's the way to think of this, if I'm going to take all the particles that were on this inside and shove them into the outside ring, I'm moving them farther out, which means I'm adding to my moment of inertia. The moment of inertia of a hollow cylinder is just mr squared, like a 1 times mr squared. I'm going to do a couple more. There are just a handful of shapes that we really use a lot. If I have a solid ball, a solid ball is a lot like a solid cylinder. I could even make it out of solid cylinders. Here is one solid cylinder, and then I could make another one, and another, and another. So I'm going to make this out of solid cylinders. The solid cylinder here on the outside, again, ball has a mass of capital M, has a total radius of r. This solid cylinder would get something like a half mr squared. This one's going to get a half mr squared, but the r is going to be a little smaller. So what I expect is that for a solid ball, I will get a smaller moment of inertia than for a solid cylinder. And that is what I get. I end up with something that is 2/5 mr squared. It's not a lot smaller, right? 2/5 is 0.4, 1/2 is 0.5, so it's not a lot smaller, but it is a little bit smaller. What about a hollow ball? A hollow ball I can make out of hollow cylinders. So if I'm going to do that, I expect that I'm going to get a smaller moment of inertia than for a hollow cylinder, but a bigger moment of inertia than for a solid ball. And that is the case. I actually get 2/3 mr squared. Just one more set. I should label this is the mass and this is the radius of the hollow ball. One more set. If I have a bar, so in some ways I'm back to that solid cylinder, but now instead of having the axis go through the cylinder this way, I'm going to have my axis go right here. This thing has a mass of m, and now because we're turning it sideways, we are going to talk about this having a length of L. This is a bar with the axis through the center. I'm going to get a moment of inertia here of 1/12 ml squared. If I take the same bar and I put the axis instead of through the center, if I put the axis through the end, I expect correctly that the moment of inertia is going to be bigger. It's going to take more to swing this bar around by the end than it does by the center. As a kid, if you grabbed a broomstick in one hand and just started spinning it around, then you would find that it spins pretty easily when you grab it by the center, but if you grab the far end of it, it takes a lot more effort to get it to spin. So this is a bar with the axis through the end, and I'm going to get 1/3 ml squared. Now I do want to generalize this a little bit. I'm going to say that the moment of inertia for some shape through the center of mass of the object, right, the moment of inertia is always going to be something or other times mr squared. For the bar, we're going to have to replace the r with an L. But something or other times mr squared, the something or other is going to depend on the shape. Or really on the mass distribution, right? For a solid cylinder, my mass is spread out pretty well. I'm going to get a gamma of 1/2. For a hollow cylinder, all my mass is at the farthest edge, so I'm going to get a gamma of 1. Solid ball, I'm getting 2/5. Hollow ball, I'm getting 2/3. Bar through the center, I'm getting 1/12. Bar through the end, I'm getting 1/3. So then you can think of that gamma as kind of an average position of where the mass is relative to the axis as a percentage of the total radius or the total length. For a hollow cylinder, which is the easy one to see, all of my mass is 100% of the distance from the axis, so my gamma comes out to be 1. For a solid cylinder, it's like a halfway point, so I get a half. For a solid ball, 40%. It's not exactly correct, but it's close, and it's a good way to think of it.